September 18, 1944. Near the German border, Hill 312. Staff Sergeant Danny Morrison watched his 3rd Sherman tank burn in 2 days. Another victim of Wehrmacht bunkers that seemed impossible to crack. The German engineers had built these fortifications with a deadly secret 90-degree entrance angles that made direct flamethrower attacks suicide missions. Every American doctrine said the same thing. Flame weapons required line-of-sight attacks at ranges under 50 yards. Get close enough to hit the bunker entrance, and German machine guns would shred you from 200 yards out at 1,200 rounds per minute. It was simple physics. Fire travels in straight lines. Walls stop fire. End of story. But when Morrison's damaged hull-mounted flamethrower accidentally sprayed burning fuel against a concrete wall, something impossible happened. The fuel didn't just dissipate, it flowed. And when it flowed around that corner, it was still burning. A former physics teacher from Iowa was about to discover that the laws of physics had just handed him a weapon no German engineer had planned for. The morning fog clung to Hill 312 like smoke from the previous day's failures, and Morrison could taste cordite in the air as he climbed out of his 3rd Sherman in 48 hours. The Wehrmacht had turned this stretch of German border into a killing field of interlocking bunkers, each one positioned to cover the approaches to the others with devastating crossfire. American tank doctrine was clear on bunker assault. Close to within 50 yards, align the hull-mounted E45 flamethrower with the entrance, and deliver a concentrated burst of burning fuel directly into the fortification. Simple, direct, effective, except when the bunkers were built by engineers who understood that Americans would try exactly that approach. Morrison's crew chief, Technical Sergeant Pete Kowalski, emerged from the smoking hull with his usual methodical calm, carrying the damaged optical sight from their main gun. Transmission's fine, engine's fine, but that 88 shell knocked out our primary gun sight and cracked the turret ring, he reported, wiping grease from his hands with a practiced motion. Hull flamethrower still operational, though. Pressure systems intact. The mathematics of their situation were brutally simple. German bunkers positioned with 90-degree entrance angles meant approaching within flamethrower range required exposing their flanks to machine gun positions 200 yards out. MG-42s firing at 1,200 rounds per minute could perforate a Sherman side armor in seconds. Morrison had calculated the angles 3 times in his notebook, hoping to find some geometric solution that doctrine had missed. There wasn't one, not with direct fire. Corporal Jimmy Chen, barely 21 and fresh from engineering school, pointed toward the bunker complex that had claimed their previous 2 tanks. Sergeant, those entrance tunnels, they're all angled at exactly 90 degrees from the main firing positions. The Germans figured out that we need line-of-sight flame attacks, so they built their bunkers to make line-of-sight impossible without getting murdered by supporting positions. Morrison nodded, studying the concrete fortifications through his binoculars. The Wehrmacht engineers had been thorough. Each bunker covered the approaches to its neighbors, creating overlapping fields of fire that turned any direct assault into a suicide run. American doctrine assumed that walls would stop flame weapons, that fire traveled in straight lines and dissipated when it hit obstacles. Physics supported that assumption. Burning fuel at 300 psi pressure behaved like any other projectile. It went where you aimed it until something solid stopped it. Sir, we could try the auxiliary flamethrower, Chen suggested, consulting his technical manual. Even with the main gun sight damage, the hull-mounted system has independent targeting. Kowalski shook his head. Same problem, kid. We still need to get within 50 yards of that entrance, and those machine gun nests will cut us apart before we can line up a shot. Morrison climbed back into the commander's position, studying the terrain between their position and the bunker complex. 300 yards of open ground, with German positions covering every possible approach route. The failed attempts by his previous crews had followed doctrine precisely: advance under covering fire, close to effective range, and deliver concentrated flame bursts directly into bunker entrances. Both times, supporting MG-42 positions had destroyed the tanks before they could complete their attacks. Let's test the whole flamethrower system, Morrison decided. Not for an attack, just to verify its functioning properly after that hit we took. They positioned the Sherman behind a concrete retaining wall that provided cover from German observation. Morrison selected a section of wall approximately 30 yards away, angled at roughly 45 degrees to their position. The mathematics should have been straightforward. Fuel stream impacts concrete, dissipates, end of engagement. He adjusted the pressure to 300 psi, aimed the hull-mounted nozzle, and triggered a 3-second burst. The burning fuel struck the concrete wall exactly as expected, but what happened next violated every assumption in American flamethrower doctrine. Instead of dissipating against the solid barrier, the fuel behaved like liquid under pressure. It flowed along the wall's surface, maintaining its burning characteristics as it followed the concrete's contours. When the wall angled around a corner, the fuel continued flowing, still burning, still under sufficient pressure to maintain effective range. Morrison stared at the burning trail that had just traveled around a corner, his physics background processing what his eyes were seeing. Fluid dynamics at high pressure treated burning fuel as a liquid projectile, not a gas. When that liquid encountered an angled surface, it maintained momentum according to the laws of physics he taught in Iowa classrooms before the war. A 45-degree deflection retained approximately 73% of the original velocity. Surface texture mattered. Smooth concrete provided cleaner deflection than rough earth or splintered wood. "Holy hell," Chen whispered, watching flames lick around the corner of the wall. "Sergeant, that fuel just shot around the building." Kowalski emerged from the tank, studying the burning path with a methodical attention he'd once applied to automotive hydraulics in Detroit. Pressure's consistent, flow rates maintaining through the deflection. It's like ricochet ballistics, but with burning liquid instead of solid projectiles. Morrison pulled out his notebook, sketching angles and calculating deflection coefficients. If burning fuel at 300 psi could maintain effective range through a 45-degree deflection, then bunker entrances positioned at 90 degrees from direct approach routes became accessible through deflected attacks. German engineers had positioned their bunkers to defeat direct line-of-sight assaults, but they'd assumed American flame weapons couldn't shoot around corners. The implications hit him like artillery concussion. Every Wehrmacht bunker complex on Hill 312 had been designed to exploit the limitations of direct flame attacks. Concrete walls that seemed like obstacles could become deflection surfaces. Tunnel entrances angled at 90 degrees could be reached with calculated deflection shots. The physics that German engineers thought protected their positions could be turned against them. Morrison closed his notebook, decision crystallizing. "Kowalski, Chen, we're going to try something that's not in any manual." Morrison spent the next 18 hours calculating fuel trajectory equations by the light of a kerosene lamp, filling pages of his notebook with angles, pressure coefficients, and deflection mathematics. Burning fuel at 300 psi behaved predictably when redirected off concrete surfaces. A 45-degree deflection angle retained 73% of original range, while steeper angles approaching 60 degrees still maintained 58% effectiveness. Surface texture proved critical to successful deflection. Smooth concrete provided clean redirection with minimal fuel dispersion, while rough earth or splintered wood scattered the stream unpredictably. The physics made sense to Morrison's teacher's mind, but battlefield application required testing with live ammunition under combat conditions. He approached Technical Sergeant Pete Kowalski during the morning equipment check, finding him elbow-deep in the hydraulic systems of their replacement Sherman. "Pete, I need you to modify our fuel pressure controls for precise adjustment between 200 and 300 psi. And I want independent flow rate controls for the hull mounted system. Kowalski emerged from the engine compartment, hydraulic fluid staining his coveralls. That's not standard procedure, Sergeant. Manual calls for maximum pressure on all flame attacks. The manual assumes direct fire at static targets, Morrison replied, showing him the calculations in his notebook. We're going to be deflecting fuel streams off concrete surfaces. Lower pressure might give us better control. Higher pressure might give us better range after deflection. I need the flexibility to adjust based on target geometry. Within 6 hours, Kowalski had jury-rigged a manual pressure control system using spare hydraulic components salvaged from damaged vehicles. The modification allowed pressure adjustment from 200 to 350 psi, with independent flow rate controls that could deliver fuel in precise bursts rather than sustained streams. It wasn't elegant engineering, but it worked reliably under the mechanical stress of tank operations. Morrison quietly recruited Corporal Jimmy Chen and Staff Sergeant Mike Rodriguez from 3rd Platoon for preliminary testing. Rodriguez commanded a veteran crew with a reputation for aggressive tactics and mechanical competence. More importantly, he understood that battlefield innovation often meant ignoring official doctrine when it wasn't working. Chen brought his engineering background and an intuitive grasp of geometric calculations that complemented Morrison's physics training. Their first controlled test took place in a bombed-out village 2 miles behind American lines, using destroyed German positions as deflection surfaces. Morrison selected a concrete wall positioned at 60 degrees to their approach route, with a simulated target 30 yards beyond the deflection point. The mathematics predicted that fuel delivered at 250 psi would retain enough velocity and burning characteristics to reach the target after deflection. Rodriguez positioned his Sherman at optimal deflection angle while Morrison calculated fuel trajectory from his commander's position. Pressure at 250, 3-second burst. Aim for the wall section approximately 4 feet from the corner edge. The fuel stream struck concrete exactly as predicted, flowing around the corner with sufficient force to reach and ignite the target position 35 yards beyond the deflection point. Son of a bitch, Rodriguez breathed over the radio. That actually works. They refined the technique through 12 separate tests, varying pressure settings, deflection angles, and target distances. Morrison documented each result in precise detail, building a database of effective parameters for different tactical situations. Optimal deflection occurred at angles between 45 and 65 degrees from perpendicular. Steeper angles caused excessive fuel dispersion, while shallow angles reduced post-deflection range below tactical minimums. Chen proved invaluable for rapid angle calculations under simulated combat stress. His engineering training allowed him to assess deflection surfaces quickly and provide accurate firing solutions within 30 seconds of target identification. Concrete wall at 52 degrees, distance to corner 18 yards. Estimate post-deflection range of 42 yards to target entrance, he would report with consistent accuracy. Word of their testing reached other crews through the informal communication networks that connected frontline units. Tank commanders began requesting demonstrations of Morrison's angle shooting technique. Staff Sergeant Bobby Walsh from 2nd Platoon watched their 4th demonstration and immediately volunteered his crew for training. We've been trying to crack that bunker line for 6 days. Lost 2 tanks yesterday using standard doctrine. If you can teach us to shoot around corners, we'll try anything. Morrison established a training protocol based on his classroom teaching experience. Each crew spent 2 hours learning deflection mathematics, followed by 4 hours of practical shooting exercises using safe practice targets. The key insight was recognizing that tunnel entrances positioned at 90 degrees from direct approach routes could be reached through calculated 60-degree deflection shots. German bunker designers had created their own vulnerability by assuming American flame weapons couldn't redirect around obstacles. Within 48 hours, Morrison had trained 6 crew teams in deflection techniques. Each crew demonstrated consistent accuracy, hitting simulated targets at ranges between 35 and 45 yards after deflection. Fuel consumption averaged 15% higher than direct fire attacks due to deflection losses, but they were achieving hits on targets that had been previously unreachable through conventional methods. The breakthrough came during their final training exercise. Morrison's team engaged a German observation post that had been harassing American supply convoys for 3 days. The position was built into a concrete foundation with the entrance tunnel angled precisely 90 degrees from any direct approach route. Standard doctrine required closing to within 50 yards of the entrance under fire from supporting positions, a tactical impossibility given the terrain. Morrison positioned his Sherman behind cover 200 yards from the observation post, using a damaged concrete wall as a deflection surface. The mathematics were straightforward. Fuel delivered at 270 psi, deflected at 58 degrees, would reach the tunnel entrance with sufficient force to neutralize the position. Chen calculated the angles, Kowalski adjusted pressure settings, and Morrison triggered a 4-second burst. The burning fuel flowed around the concrete corner exactly as physics predicted, entering the tunnel entrance and neutralizing the German position within seconds. 3 Wehrmacht soldiers emerged with their hands raised, reporting later during interrogation that they had never expected American fire weapons that could shoot around buildings. Morrison's technique had just achieved something that conventional doctrine said was impossible. German defensive positions designed to exploit the limitations of direct flame attacks had become vulnerable to deflected fire from angles their engineers never considered. The mathematics of fluid dynamics had turned concrete obstacles into tactical advantages. Lieutenant Colonel James Hayes arrived at Morrison's position on September 25th with intelligence reports that transformed their tactical experiment into operational necessity. The Siegfried Line's Sector 7 contained 23 separate bunker fortifications connected by underground tunnel networks, defended by veteran elements of the German 275th Infantry Division. American forces had been stalled for 8 days attempting conventional assaults, with casualty rates approaching 40% for units engaged in direct bunker attacks. Sergeant Morrison, I've been watching your deflection technique results, Hayes said, spreading tactical maps across the hood of his Jeep. Battalion needs those bunkers cleared in 48 hours. Can you train enough crews to make this work on a larger scale? Morrison studied the intelligence photographs showing bunker positions across a 2-mile front. Each fortification followed the same engineering principles that had made Hill 312 nearly impregnable, entrance tunnels angled at 90 degrees from direct approach routes, with interlocking machine gun positions covering all conventional attack corridors. German engineers had applied lessons learned from 8 months of American bunker assaults, creating defensive positions that exploited every limitation of standard flamethrower doctrine. Sir, I can train 6 crews in deflection techniques within 36 hours. Each crew will need 4 hours of mathematical instruction followed by 8 hours of practical shooting exercises. The key is teaching them to read deflection surfaces and calculate angles under combat stress. Hayes authorized the expanded training program, assigning Morrison temporary authority to modify equipment and ammunition loadouts for participating crews. Technical Sergeant Kowalski supervised hydraulic pressure modifications across 12 Sherman tanks, installing manual pressure controls that allowed adjustment between 200 and 350 psi. Each modification required 6 hours of mechanical work using salvaged components from damaged vehicles. Morrison established his training site in a bombed German village 4 miles behind American lines, using destroyed concrete buildings as deflection surfaces for live fire exercises. He divided instruction into 3 phases based on his teaching experience in Iowa. Phase 1 covered deflection mathematics, angle calculation, pressure settings, and fuel conservation techniques. Phase 2 involved static target practice using concrete walls and simulated bunker entrances. Phase 3 simulated combat conditions with moving targets and time pressure. Corporal Jimmy Chen proved essential for rapid crew training, his engineering background allowing him to explain angle calculations in practical terms that veteran tank commanders could apply immediately. "Think of it like bank shots in pool," he told Staff Sergeant Walsh's crew during their first session. "The fuel follows physics just like a cue ball. 45-degree angle gives you maximum distance after deflection. Steeper angles give you more accuracy but less range." The mathematics became routine through repetition. Concrete walls at 50 to 60 degrees from perpendicular provided optimal deflection characteristics. Fuel delivered at 250 to 270 psi retained sufficient velocity to reach targets 35 to 40 yards beyond the deflection point. Surface assessment took 30 seconds. Smooth concrete gave clean deflection. Rough masonry scattered fuel unpredictably. Splintered wood absorbed too much energy for effective redirection. Staff Sergeant Bobby Walsh mastered the technique fastest, his crew achieving 85% hit rates on deflected targets within 24 hours of training. It's like indirect artillery, but with burning liquid instead of explosives, he reported during their final qualification exercise. "Once you understand the angles, it becomes as reliable as direct fire." Morrison documented standard operating procedures for deflection attacks in a field manual he wrote during overnight sessions. Key principles included surface reconnaissance before engagement, pressure adjustment based on deflection angle and target distance, and fuel conservation through controlled bursts rather than sustained streams. Each crew received laminated calculation cards showing deflection angles, pressure settings, and estimated fuel consumption for common tactical situations. Intelligence reports from German prisoners captured during preliminary actions revealed that Wehrmacht defenders had never encountered flame attacks from impossible angles. "The Americans have fire weapons that shoot around buildings," reported a sergeant from the 275th Infantry who had survived Morrison's attack on the observation post. German tactical manuals contained no countermeasures for deflected flame attacks because their engineers had assumed such attacks were physically impossible. By September 27th, Morrison had trained 12 crew teams to operational proficiency in deflection techniques. Final qualification exercises demonstrated consistent accuracy against simulated bunker targets, with average engagement times reduced from 45 minutes per position using conventional doctrine to 18 minutes using deflected fire. Fuel consumption per successful bunker clearance dropped from 290 gallons to 190 gallons, extending operational range significantly. The psychological impact on participating crews was transformative. Tank commanders who had watched their units suffer devastating casualties attempting conventional bunker assaults now possessed a technique that allowed engagement from positions of relative safety. Crew exposure time during bunker attacks was reduced by 60%, eliminating the suicidal close-range approaches that conventional doctrine required. Morrison's final briefing to participating crews emphasized the limitations of deflection attacks alongside their advantages. "This technique works because German engineers didn't plan for it," he explained to the assembled tank commanders. "Surface conditions matter. Wet concrete gives different deflection characteristics than dry surfaces. Wind affects fuel trajectory after deflection. And remember that we're consuming 15% more fuel per engagement, so ammunition discipline becomes critical during extended operations. Lieutenant Colonel Hayes reviewed the training results with satisfaction tempered by awareness of the stakes involved. Sector 7 represented the strongest German defensive position in their operational area, with bunker complexes that had resisted assault for over a week. Success would open a corridor through the Siegfried Line that could accelerate the entire offensive timeline. Failure would result in continued stalemate and mounting casualties from conventional attacks. The night before the main assault, Morrison found himself calculating and recalculating deflection angles for each bunker position identified in intelligence reports. His notebook contained detailed firing solutions for 23 separate targets with backup calculations for alternative approach routes if primary deflection surfaces proved unsuitable. The mathematics were solid, the training was complete, and his crews had demonstrated consistent proficiency during exercises. At 0500 hours on September 28th, 12 modified Sherman tanks moved into assault positions for the attack on Siegfried Line, Sector 7, carrying weapons that could shoot around corners and crews trained to exploit German engineering assumptions that no longer applied. Dawn on September 28th broke gray and cold across Sector 7, with morning mist clinging to the concrete fortifications that had held up American advances for 8 days. Morrison positioned his Sherman behind a damaged stone farmhouse 200 yards from Bunker Complex Alpha, studying the target through binoculars, while Kowalski made final adjustments to their pressure systems. Intelligence photographs had identified 5 interconnected positions defended by veteran Wehrmacht troops, but the reality of the terrain presented deflection opportunities that aerial reconnaissance had missed. The first bunker fell exactly as training had predicted. Morrison calculated a 57-degree deflection angle using a concrete retaining wall, delivered fuel at 260 psi, and watched burning liquid flow around the corner into the tunnel entrance with mathematical precision. German defenders emerged within 90 seconds, hands raised, reporting later that they had never expected American fire from that angle. Staff Sergeant Walsh's crew neutralized the second position using identical techniques, achieving successful deflection off a damaged concrete foundation. American infantry advanced 400 yards in the first hour of the assault, their fastest progress since the Siegfried Line offensive began. Morrison's deflection teams were clearing bunker positions in an average of 12 minutes each, compared to the 45-minute engagements that conventional doctrine required. German resistance appeared to collapse as defending units encountered flame attacks from angles their engineers had deemed impossible. The third bunker required more complex calculations due to irregular deflection surfaces, but Chen's rapid geometric assessment provided accurate firing solutions within 30 seconds. Morrison adjusted pressure to 240 psi to compensate for the steeper deflection angle, delivered a controlled 4-second burst, and achieved successful target neutralization without exposing his Sherman to defensive fire. Wehrmacht prisoners from this position reported complete bewilderment at American flame weapons that violated the laws of physics. Radio communications between participating crews reflected growing confidence as the deflection technique proved reliable under actual combat conditions. Alpha 2 to Alpha 1. Bunker neutralized using 62-degree deflection, textbook results, reported Rodriguez from 2nd Platoon. Alpha 4 to all units. German prisoners are asking how we're shooting around concrete walls, Walsh added with obvious satisfaction. Morrison monitored these transmissions while calculating approach angles for Bunker 4, the largest position in Complex Alpha. Intelligence had identified Bunker 4 as the command center for the sector's defensive network, built into a natural hillside with reinforced concrete walls 3 feet thick. Morrison positioned his Sherman to utilize a damaged bridge foundation as a deflection surface, calculating that fuel delivered at 280 psi would retain sufficient velocity to reach the tunnel entrance 43 yards beyond the deflection point. The mathematics were more complex than previous engagements, but still within established parameters for successful deflection attacks. Chen verified the angle calculations while Kowalski adjusted pressure settings to Morrison's specifications. Deflection surface at 59 degrees, target distance estimated at 41 yards post-deflection. Surface conditions appear optimal for clean redirection, Chen reported, with the precision that had made him invaluable during training exercises. Morrison aligned the hull-mounted flamethrower with careful attention to the calculated impact point on the concrete deflection surface. The fuel stream struck the bridge foundation exactly where Morrison had aimed, flowing around the corner with the fluid dynamics that physics predicted. But what happened next violated every assumption about German bunker construction that American intelligence had made. Instead of neutralizing defending troops, the burning fuel ignited an ammunition cache that Wehrmacht engineers had positioned in the tunnel system for rapid resupply during extended sieges. The explosion shattered concrete walls, collapsed portions of the underground tunnel network, and created a debris field that extended 50 yards beyond the bunker entrance. Morrison watched through his periscope as smoke and dust obscured the entire target area, realizing immediately that something had gone catastrophically wrong. The controlled engagement that should have lasted 4 minutes had become a demolition event that violated every principle of precision warfare. American infantry, who had been advancing to secure the neutralized position, found themselves trapped in collapsed tunnel sections, buried under concrete debris that the explosion had displaced. Radio communications from forward units reported 8 men missing in the underground passages, their locations unknown, and rescue access blocked by structural collapse. Morrison's mathematical precision had created a disaster that conventional doctrine would have avoided. Lieutenant Colonel Hayes arrived at Morrison's position within 20 minutes, his expression reflecting the weight of command decisions that had cost American lives. "Sergeant, what happened here?" Intelligence reports indicated standard bunker construction, not ammunition storage in the tunnel network. Morrison showed him the calculation sheets and deflection angles that had worked perfectly for the previous 3 bunkers, trying to explain why identical techniques had produced such different results. The investigation revealed that German engineers had modified ammunition storage procedures for command bunkers after American flame attacks began achieving success against standard positions. Instead of storing explosives in separate underground magazines, they had positioned ammunition caches directly in tunnel approaches to maximize defensive firepower during extended engagements. Morrison's deflected fuel had ignited these caches, creating explosions that bunker designers had never intended. Chen's post-engagement analysis confirmed that the deflection technique itself had functioned exactly as predicted. Fuel trajectory, pressure settings, and angle calculations had produced textbook results. The disaster occurred because American intelligence had failed to identify German modifications to ammunition storage protocols, not because deflection attacks were inherently flawed. "The mathematics were perfect, Sergeant," Chen reported with obvious distress. "We just didn't know what we were shooting at." Staff Sergeant Walsh's crew had been positioned to provide covering fire during Morrison's engagement, witnessing the explosion that trapped 8 American infantrymen in collapsed tunnels. "Never seen anything like that, Morrison. Your fuel hit exactly where you calculated. Then the whole damn bunker went up like an ammunition depot." Walsh's report confirmed that deflection accuracy had not caused the casualties. Inadequate reconnaissance of German defensive modifications had. Morrison spent the remainder of September 28th calculating and recalculating the explosion that had killed 8 men who trusted his innovation, his notebook filled with geometric analyses of the incident, searching for mathematical explanations that might have predicted the ammunition cache ignition. But the physics of deflected flame attacks could not account for German engineering decisions that intelligence reports had failed to identify. Battalion Command suspended deflection attacks pending investigation of the incident, returning participating crews to conventional bunker assault doctrine. Morrison was relieved of his experimental responsibilities, his technique deemed too unpredictable for continued tactical use. The innovation that had promised to revolutionize bunker warfare had claimed the lives of the men it was designed to protect. Morrison spent September 29th in a foxhole behind American lines, filling pages of his notebook with calculations that refused to change no matter how many times he reworked them. The deflection angle had been 59 degrees, fuel pressure 280 psi, target distance 41 yards post-deflection. Every variable had fallen within established parameters for successful bunker neutralization. The mathematics that had failed 8 American soldiers were identical to the mathematics that had saved dozens of others during previous engagements. Technical Sergeant Kowalski found him there at 1400 hours, carrying intelligence reports from German prisoners captured during the morning's conventional assaults. "Sergeant, you need to see this. Wehrmacht engineers have been modifying ammunition storage in command bunkers since our deflection attacks started working. They're positioning explosive caches directly in tunnel approaches instead of separate underground magazines." The intelligence revealed systematic changes to German defensive doctrine that American reconnaissance had failed to detect. Standard bunker positions maintained ammunition supplies in reinforced storage areas separated from living quarters and defensive positions. Command bunkers, however, had begun storing artillery shells and explosive charges directly in entrance tunnels to maximize firepower during extended sieges. Morrison's deflected fuel had encountered ammunition caches that existed in violation of previous German engineering practices. Morrison studied the prisoner interrogation transcripts with growing understanding of what had gone wrong. The deflection technique itself remained mathematically sound. Fluid dynamics at controlled pressures produced predictable results when applied to concrete surfaces. The disaster had occurred because his reconnaissance focused on physics while ignoring German tactical adaptations to American innovations. He had been so proud of solving the mathematical puzzle that he had forgotten to verify what his mathematics were being applied against. By October 1st, Morrison had developed modified deflection protocols that incorporated intelligence assessment alongside geometric calculations. Lower pressure settings of 200 psi reduced fuel ignition temperatures, minimizing the risk of explosive detonation in ammunition-rich environments. Shorter fuel bursts of 2 seconds instead of 4 prevented accumulation of burning liquid near potential explosive caches. Most importantly, intelligence teams would precede all deflection attacks to identify non-standard bunker modifications. Morrison requested permission from Lieutenant Colonel Hayes to test his refined approach on a German observation post that had been harassing American supply convoys since the Sector 7 assault. The position was built into a concrete foundation with standard defensive characteristics, no ammunition storage in tunnel approaches, no modification to established Wehrmacht construction practices. Hayes approved the limited test, but with strict conditions. Maximum pressure of 200 psi, engagement time limited to 90 seconds, and immediate withdrawal if unexpected results occurred. The test engagement on October 2nd demonstrated that modified deflection techniques retained tactical effectiveness while reducing explosive ignition risks. Morrison's crew neutralized the German position using controlled fuel bursts at reduced pressure, achieving successful target elimination without structural collapse or unexpected detonations. German defenders reported during interrogation that American flame attacks remained impossible to predict or counter, even with reduced fuel pressure. Staff Sergeant Walsh volunteered his crew for additional testing of Morrison's refined protocols, having witnessed both the success of deflection attacks and the tragedy of the ammunition cache explosion. "Morrison, your technique saved my crew 3 times before that disaster happened. If you figured out how to make it safer, we'll try it again." Walsh's crew achieved successful bunker neutralization using 200 psi pressure settings and 2-second fuel bursts, proving that reduced parameters maintained tactical effectiveness. Intelligence teams led by Corporal Chen began conducting detailed reconnaissance of bunker positions before deflection attacks, identifying ammunition storage modifications and non-standard defensive features that could complicate fuel deflection. Their assessment process required an additional 30 minutes per target, but provided critical information about German engineering adaptations that American forces had not previously considered. "We're not just calculating angles anymore," Chen explained to participating crews. "We're reading German tactical evolution." Between October 2nd and 4th, Morrison's refined deflection technique cleared 11 German bunker positions across different sectors of the Siegfried Line without a single American casualty. Average engagement time increased to 15 minutes due to additional reconnaissance requirements, but remained significantly faster than conventional assault doctrine. German resistance began collapsing as defending units encountered flame attacks from calculated angles that their defensive planning could not counter. Fuel efficiency improved dramatically with reduced pressure settings and controlled burst techniques. Average fuel consumption per successful bunker clearance dropped to 160 gallons, compared to 290 gallons required for conventional direct assault. Morrison's crews could engage more targets per operational day while maintaining tactical effectiveness against German defensive positions. The psychological impact on German defenders became evident through prisoner interrogations conducted by military intelligence. Wehrmacht troops reported that American flame attacks violated fundamental assumptions about defensive positioning and concrete obstacles. "The Americans shoot fire around corners like artillery shoots over hills," reported a German sergeant captured during the October 4th actions. "Our bunkers protect us from direct attack, but not from burning liquid that flows like water." Lieutenant Colonel Hayes reviewed Morrison's revised technique with the careful attention of a commander who had learned to balance innovation against responsibility. The modified protocols addressed the reconnaissance failures that had caused the ammunition cache explosion while retaining the tactical advantages that made deflection attacks effective. "Sergeant Morrison, your refined approach appears to solve the intelligence problem that caused our casualties. I'm authorizing expanded implementation with specific emphasis on pre-engagement reconnaissance." Morrison established new training protocols based on lessons learned from the Bunker 4 disaster. Each crew received 8 hours of intelligence assessment instruction alongside the geometric calculations and pressure control techniques. The key insight was that innovation without comprehensive situational awareness was merely cleverness, but innovation combined with thorough reconnaissance could change tactical realities. By October 10th, Morrison had trained 18 crew teams in refined deflection techniques, with each crew demonstrating proficiency in both angle calculations and intelligence assessment. German bunker complexes across a 4-mile front began falling to American advances as deflection attacks eliminated defensive positions that conventional doctrine could not reach. On October 12th, Morrison received the Silver Star from Lieutenant Colonel Hayes in recognition of tactical innovation that had revolutionized American bunker assault capabilities. His deflection technique was approved for division-wide implementation and incorporated into revised Flamethrower doctrine for future operations. German defensive planning began accounting for deflected flame attacks acknowledging that American innovation had permanently altered the tactical calculus of fortified warfare. The 8 men who died in collapsed tunnels at Bunker 4 were remembered not as casualties of failed innovation, but as soldiers whose sacrifice taught Morrison that mathematical precision, without complete situational understanding, was insufficient for responsible tactical leadership.